Hello. I was streaming a few minutes ago, but then the internet cut out. So I restarted my stream. Anyways, I only streamed for like 5 minutes. So I was learning calculus 3. I was revising the last chapter. Hold on, let me change to full screen. So last stream I did directional derivatives on the gradient, and this stream I'm planning to finish 4.7 and 4.8, minima maxima and Lagrange, I think that's how you pronounce it. So, okay, let me just quickly revise this and then I will go to the next chapter. We start with the graph of a surface defined by the equation c is equal to f of xy. Given a point AB in the domain of f, we choose a direction to travel from that point. So a random point and choose a direction to travel. We measure the direction using the angle theta, which is measured clockwise in the xy plane. Okay. Starting at 0 from the positive x-axis. So positive x-axis. So angle is like this direction, right? The distance we travel is h. So the distance of this is h. The direction we travel to is given by the unit vector u cos theta I plus sine theta j. Therefore, the z coordinate of the second point of the graph is given by z is equal to f of. So the new point is a plus h cos theta, and the new y point is b plus h sine theta. So I was saying in my previous stream, like this green line is this green arrow is what is the point we travel. We start from this point, and these dashed lines are touching the planes. It gives you an idea where the point is. I should draw a dashed line over here as well. So the new point is here. And here. And here. Okay, let's say this is the new point. Now, the distance we travel is h, but I personally think it's like h in the xy plane. It's like h in, like let's say we extend the line touching the xy plane. Yeah. So I think it's only like this arrow is parallel to the xy plane, the orange arrow. I think h, the distance we travel is h. I think h is only in the xy plane. It's not considering the z axis. Then it would make sense that the new x is h cos theta, and then the new y is plus h sine theta. So we started AB, which is over here. Distance we travel in the xy plane is h. So the new z value is the new z value, new z point. So the original, it's like a, b, and f of ab. So x, y, and z. Z is f of ab. And then the new point is f of, the new z point is f of a plus h cos theta. Do we add I? No, there's no I or j. And then the new y value is b plus h sine theta. But this equation would only make sense as h is like defined in the parallel to the xy plane. Then the direction derivative of f in the direction of u is given by this. Okay. So we have this curve defined by z. Z is equal to f of xy. And the instant in a particular u direction, the instantaneous change in z, yeah, the instantaneous change in z would be given by directional derivative. So directional derivative in the direction of u of f of ab. So we start at point ab. We start at point ab, and the instantaneous change of z when you are going in the direction of u would be given by the change in z, right? So this is the new z. This is the old z. Change in z. This is the new z in the direction of u divided by h. We take the limit to 0. I did the exercise the last stream, so I'm not going to be doing it this stream. Direction derivative of a function of two variables. Let z is equal to f of xy be a function of two variables x and y, and assume f of partial derivative of f with respect to x and the partial derivative of f with respect to y exist, and f of xy is differentiable everywhere. Then the direction derivative of f in the direction of u is given by this. Okay. So f of xy in the direction of u is given by partial derivative of x of f with respect to x, and then cos theta is a plus. Yeah. Partial derivative of f with respect to y in the direction in with respect to y times sine theta. What else did we learn? The vector is called the gradient of f and is defined like this. The vector is also written as grad f. Okay, from my understanding, grad f would be we aren't choosing the direction. If we do an instantaneous increase of both x and y, whatever the new value of c is, whatever the change in the value of c, I think that's grad f. Grad f is different because we aren't choosing the direction. We are just doing an instantaneous change of x and y. If I'm wrong, please correct me. The angle between grad f x naught and y naught and u cos theta I plus sine theta j is phi. We have this. So vector A dot product vector B, length of A, length of B, cos theta, right? Cos phi. Phi is two vectors, AB is phi. If the angle between this and the direction vector is phi, so the instantaneous change of z with respect to the instantaneous change of x and y, the angle between that vector and vector u is phi. We have where did this come from? So this is defined like this. Where did this come from? So we are defining grad as this. So, okay, wait, I understand. So u, did I define u? No, I didn't. U is cos theta I cos theta I plus sin theta j. And then grad f is this, right? In the I direction, in the y direction. And then we do dot product. So we multiply their components. Dot cos theta sin theta. And that gives this. This is read as del f. Isn't that read as grad f? Is it del? Is it both? Anyways, so we have this. So if du is this, if du is this, then let's say the angle between them is phi. So we have plus it with, but the magnitude of u is 1. So we are left with this. So 0 change in f. Okay, we have minus delta f. Okay, plus delta f. All right. Most rapid increase in f. Most rapid decrease in f. The maximum value of near f of x naught and x naught y naught is delta the magnitude of grad f. Because cos phi is 1. So phi, so yeah, phi would be 0, right? And if u is over here, then cos phi is 90. And then the direction vector is 0 because there's no change in c. Gradients and level curve. Level curve is like it's like all the points where z has the same value, right? Level curves. Okay, anyways, let's go to the next chapter. Minima and maxima problem. For functions of a single variable, we define the critical points as the values of the function where the derivative equals 0 or does not exist. For functions of two or more variables, the concept is essentially the same except the fact that you're now working with partial derivatives. Let c is equal to f of xy be a function of two variables that is defined on an open set containing the point x naught, y naught. The point x naught, y naught is called a critical point of a function of two variables f if one of the two following conditions hold. So both partial derivatives 0 and either of these does not exist. What happens if both of them don't exist? Find the critical points of each of the following functions. Example 4.38. Copy. And also let me just open Desmos. Desmos. Find the critical point. A and this is B. Let's try A first. F of x is this. Now, is there no, never mind. Uh, Partial derivative. Uh, I think it's easier to write it like this. Is we take all this, we do the chain rule. Let's say, wait, before I do this, let's say g of xy is all this. Y plus 36 x plus 36, then partial derivative with respect to x. Why is this taking so long? This would be 0 minus 18 x 0 plus 36. Partial derivative with respect to y plus 24. And I forgot the chain rule. Hold on. H of x, y actually h of I forgot how you do this. Let me think. Is the partial derivative of all this with respect to x, right? Plus 36. So now we use the chain rule, right? Why am I getting confused? Hold on. Want to review the chain rule again. So partial derivative with respect to u is x, and then x with respect to u plus z, y, and then y with respect to u. What if it's with respect to g of x, y? I was originally thinking of putting x, y, g of x, y over here. Never mind. So is it like a derivative of the outside? This is to the power of half, so it becomes minus half, then times it by. I don't feel like this is correct. Minus the partial derivative of the inside. minus 18 x plus 36. Okay, apparently this is what we are supposed to do. But if we equate them to 0, or it will become easier, right? Then we will be left with minus 9x. Okay. Uh, let's do the next one. I thought I was going the wrong path. G of xy. X squared plus 2xy minus 4y squared plus 4x minus 6y. Two x plus 2y plus 4. And then in the y direction, we have 2x minus 8y minus 6. And then we need to check where there's 0, right? Yeah. This needs to be 0. If I subtract these two, 2 minus minus 8 or minus minus 6. So y is equal to 1. If y is 1, 4 plus 2 is 6, x is 3. Is that correct? Y is equal to 1. Y is equal to negative 1 actually. Y is equal to negative 1. Then x is equal to positive 1. The main purpose of determining critical points is to locate relative maxima and minima as in single variable calculus. In working with a function of one variable, the definition of local extremum involves finding an interval around the critical point such that the function value is greater than or less than all the other function values in that interval. When working with a function of two or more variables, we work with an open disk around that point. Let C be a function of two variables that is defined and continuous on an open set containing the point x naught, y naught. Function has a local maxima at x naught, y naught if this condition is true for all points within some open disk centered at x naught, y naught. And it's a local maximum if this is true for all points within some disk centered at x naught, y naught. So z is equal to root 16 minus x square minus y square. This graph has a maximum value when x, y is 0. It attains its minimum value at the boundaries of its domain, which is x squared plus y squared is 16. Also the set of all these values. Fermat's theorem for functions of two variables. Let C is equal to f of xy be a function of two variables that is defined and continuous on an open set containing the point x naught y naught. Suppose x and y, the partial derivative of x with respect to partial derivative of f with respect to x and partial derivative of f with respect to y each exist at x naught y naught. If f has a local extremum at x naught y naught, then x naught y naught is a critical point of f. Consider the function f of x is equal to x cubed. This function has a critical point at x is equal to 0. However, f does not have an extreme value at x is equal to 0. And an x cubed critical point extremum is like a minimum or a maximum value, right? And then critical point is where the derivative is 0. So I think extremum is like uh, if we have a graph like this, these are all critical points, but this here is an extremum because it's like, suppose this is the local range, this is the extremum, and this is the extremum, right? The existence of a critical value at x is equal to x naught does not guarantee a local minimum at x is equal to x naught. Okay, we have a critical point over here because the derivative is 0, but it's not an extremum. Same is true for a function of two or more variables. One way this can happen is at a saddle point. Example of a saddle point appears in the following figure. This graph is kind of confusing. So is it like going back? X square minus y square. Let's try like a 3D graph. In this graph, the origin is a saddle point. This is because of first partial derivative. We are both equal to 0 at this point, but it is neither a maximum nor a minimum for the function. Furthermore, the vertical trace corresponding to y is equal to 0 is z is equal to x square, a parabola opening upwards. But the vertical trace corresponding to x is equal to 0 is z is equal to minus y square, a parabola opening downwards. Therefore, it is both a global maximum for one trace and a global minimum for another. Z is equal to x square minus y square. Can I make it transparent? So, this is quite laggy. Can I determine how translucent? Okay, this taking. And that was so laggy. Anyways, if I do what? Y is equal to 0. That is at this point right here. Then we have a parabola going downwards. So for this 2D shape, this would be a maxima, right? And if I do x is equal to 0, so this line right here, if I cut it at this point, then I get this 2D trace where this is a minima. But in the 3D graph, it's neither a minima or a maxima. Given a function z is equal to f of x, the point x naught y naught f of x naught y naught is a saddle point if both partial derivative with respect to x is 0 and with respect to y is 0, but f does not have a local extremum at x naught y naught. The second derivative test for a function of one variable provides a method for determining whether an extremum occurs at a critical point of a function. Wait, hold on. How would it, hold on. So x cube is like this, right? The derivative is 3x squared. The double derivative is 6x. Oh, if the double derivative is 0, it's neither a minimum or a max. It's not an extremum point, right? When extending this result to a function of two variables, an issue arises related to the fact that there are, in fact, four different second order partial derivatives. Although equality of mixed partials reduces this to 3, the second derivative test for a function of two variables stated in the following theorem uses discriminant d that replaces a double derivative of f in the second derivative test for a function of one variable. So let z be a function of two variables for which first and second order partial derivatives are continuous on some disk containing point x naught y naught. Suppose f of x naught y naught is 0 and f of y x naught y naught is 0. Define the quantity d if d is more than 0 and f of x is more than 0, then f has a local minimum. If f of x is less than 0, then f has a local maximum. If d is less than 0, then f has a saddle point at x naught y naught. Shouldn't we consider fyy as well? If d is equal to 0, then the test is inconclusive. So local minima, local maxima, and saddle point. Let z is equal to f of xy be a function of two variables for which the first and second ordered partial derivatives are continuous on some disk containing the point x naught y naught. To apply the second derivative test to find the local extrema, use the following steps. Determine the critical points, calculate the discriminant, apply the second derivative test. Okay, this is quite confusing. So, copy this. It doesn't even copy properly. Where did it go? Okay, we have. Why is it so laggy? It's not. Hold on. Capture screen area, maybe. Capture screen area works better than the whatever than the other options. Okay, anyways. We have this. What exercise is this? 4.39. F of x, x, y. We have 8x plus 8. Eighteen y minus 36. Now, so 8x plus 8 is equal to 0. We need to find the critical point, which would imply x is negative 1. 18y minus 36 is 0. Should imply y is 2. So we found the critical point. Now comes the hard part. Finding the second derivative. F of x this is like we find it with respect to x, then we find it with respect to y, right? Which would be 0. This would be 18. This would be 8. And then d would be 18 times 8. 18 times 8. This is more than 0, and this is definitely more than 0. A local minimum. So is that correct? Yeah, a local minimum at negative 1 and 2. At 2? Yeah. When finding a global extrema of a function of one variable on a closed interval, we start by checking the critical values over that interval and then evaluate the function at the endpoints of the interval. Wait, hold on. Extrema is like any point where the derivative is not any point where it's like maxima over a small interval, right? So this here would be a global maxima, This would be a global maxima in this entire interval. This would be a local global minimum in this entire interval. So this would be local minimum. These here would be local maximum. Uh, when working with the function of two variables, a closed interval is replaced by a closed bounded set. A set is bounded if all the points in that set can be contained within a ball of finite radius. First, we need to find the critical points inside that set and calculate the corresponding critical values. Then it is necessary to find the maximum and minimum value of the function on the boundary of the set. When we have all these values, the largest function value corresponds to the global maximum and the smallest function value corresponds to the absolute minimum. Extreme value theorem. A continuous function of closed bounded set T in the plane attains an absolute maximum value at some point of T and an absolute minimum value at some point of T. Okay. Given that the function is continuous, right? Assume z is equal to f of xy is a differentiable function of two variables defined on a closed bounded set T. Then f will attain the absolute maximum value and the absolute minimum value, which are respectively the largest and smallest values among the following. The values of f at a critical point, at the critical points of f in T. Oh, so out of all the values over here, at the critical points and at the boundaries, one of them has to be absolute maximum and one of them has to be absolute minimum, given that the function is continuous. So determine critical points, calculate f at each of these critical points, determine the maximum minimum values, the boundaries of its domain. On the domain defined by 0. Okay, let's try this. Add to clipboard. Why does this work so much better? So example 4.40. On the domain defined by, so, okay, f with respect to x is this 2x minus 2y minus 4, right? And then with respect to y, it's minus 2x plus 8y minus 2. Is equal to 0, but I can half it. And then I can half this as well. So we have this. We can add them. So x not cancel out. We are left with 3. Y not is equal to 2. Is this even correct? I feel like it should be a whole number. Hold on. 2x minus 2y minus 4. Okay, and then we have minus 2x plus 8y minus 2. 0. If this is equal to 0. 2 minus 2 minus 4. You have 1, 1, 2. Okay. Minus 2, 8 minus 2. 1, 4, 1. Minus 1 plus 4 and then plus 1. Sorry, minus 1. This goes this side. Then we add them. We get 3. 0 x naught 5. 5 minus 3 2. So this is a critical point. However, they defined this domain, right? Y is valid but x is not valid. So this is causing an issue. Okay, so what are the boundaries of x and y? Hold on. We have 0 4 and 0 2. X, no, this is y. 0 0 0 for y square minus 2y plus 24. And then we have x 0, 0 0, no, y 0. So 0 0 0 x square minus 4x plus 24. The biggest value of y is 2. Hold on a minute. Okay, never mind. X and 2 x squared minus 4x minus 4x minus 4x minus 8x plus 4 times 4 plus it with 24, right? Sixteen 40. I don't understand why I'm doing this. I'm checking the boundary points. The only time both the derivatives are 0 is at this point, right? Hold on, let me go check. Find the critical points of f. Calculate at f at each of these critical points. Determine the maximum and minimum values of f at the boundary of its domain. Okay, that's what I'm doing right now. We have 4 square is 16 minus 8y plus 4y square minus 10y, and then 40. Now what? Do we find the derivative at each point? Do we find the critical points on each of these points? So with respect to y, critical point, this would be minus 2, and then y naught here would be 1 over 4, and we have x 2x minus 4. So the critical point here would be 2. Critical point here would be 4. And then lastly, the critical point, no wait, I need to derive this. Minus 10 plus 8y, 10 over 8. We have 0, 1 over 4, 0, 2. Okay, we can't consider this, but we can consider these, right? So we have 0, 1 over 4. We have 2, 0. Hold on, no, I need to plug this back into f and calculate the lowest f value, right? Okay, wait, hold on. I'll just use a calculator. F of x, y is equal to x square. Remove this. Is equal to x square minus 2x plus 4y. Minus 2xy plus 4y square. Is this correct? Minus 4x minus 2y plus 24. Is this correct? Okay, so let's do f of 0 and 1 over 4. Now let's do f of 2 and 0. 4 and 2. 4 and 10 over 8. So x is from 0 to 4. The lowest point is over here, 4 and 10 over 8. Let's see what they have. They got this. We can't count. Wait, hold on. What they're saying is, we have one. Oh, x naught is 3. I made a mistake here. So now if I plug in 1 and 3, this is the highest point. This is the maxima. Hold on. What's the issue here? X square minus 2xy plus 4y square minus 4x minus 2y plus 24. So they calculated the corner points, right? I think what I did over here wasn't right. Calculated the no, not the corner points. You have to calculate the lowest point in the entire thing, right? Two zero with 20, 4 2 with 20, 0 2 and 0 2. How did they get 0 2? Four minus 2y plus 24. Line segment containing okay, 5 over 4 is correct. 4 and 5 over 4. 4 2 is the issue. No, 4 2 is not the issue. 4 2 2 0 4 5 over 4. 4 0 4 2 0 4 5 over 4 and 4 2. 2 0 4 5 over 4 and 4 2. It's this one is the issue, I think. No, it's 0 1 over 4. That's correct. So You also need to find the values of f of xy at the corners of its domain. Uh, okay, these are all the corners. I think I did not do this part where I had to find the corners. But even with the corners, the highest value is 45, right? Absolute maximum value is 36. F of 3, 1 is 70. F of... I did this wrong. 3, 1 is 17. This is the lowest value, even including the corners. The highest value they calculated over here is 36. This took so long. Okay, anyways, I was planning to do the next chapter this stream, but I think I will leave it up to the next stream. So I will end the stream here. And yeah, I'm gonna see you guys next time. Bye.